In this second video, I want us to continue analyzing functions, but now analyzing discontinuities. What are the three types of discontinuity that we're going to be dealing with here in calculus? I have type 1, removable discontinuity, right here. Type 2, a jump discontinuity. And type 3 will be infinite discontinuity. So these are the three types of discontinuities. Let's go over each type separately so that we can write formally what does it mean for a function to have a removable discontinuity. So in the first graph right here that we have, you notice that this particular graph has a limit at 0.5, nicely, but it is not continuous. In other words, it is discontinuous because the limit does not equal to f of 0.5. The limit is equal to 1.5 at 0.5, but f of 0.5 is 1, not 1.5. So this type of discontinuity is called removable. Informally, in pre-calculus classes, we call it a hole discontinuity, that there is a hole. In calculus, though, we're going to not call it a hole discontinuity, we're going to call it removable discontinuity. Let's go ahead and start stating the formal definition of a removable discontinuity. I already started with the preliminary conditions here. So I have a function f has a removable discontinuity. Let me underline removable. This is what we're trying to define. At x equals a, if and only if the following is true. The limit as x approaches a of f of x exists, but is not equal to f of a. Or maybe f of a does not exist. That really means it could be that there is just a hole. There is no dot above or below, just a hole. In other words, f is undefined at x equals a. And just to give you a visual, imagine that practically you have the same graph as above, but then you have a hole there, an open circle, and no dot above or below. Well, this hole is enough for us to have a removable discontinuity, right? That's what removable discontinuity really means, that the limit exists at a particular value of a. Wonderful, the limit exists. But for some reason, it doesn't equal to f of a if f of a exists, because maybe it is equal to some other value below or above the curve. Or, like in this case, f is completely undefined at a. There is no dot above or below. So this is another illustration of a removable discontinuity. Now, let's look at type 2, which is called a jump discontinuity. This is where you're tracing along the graph, you get here, and then all of a sudden, boom, you have to jump to be able to continue tracing along the graph. Which is really telling us that the left-hand limit and the right-hand limit are unequal. There is no connection at all with the left part of the graph and the right part of the graph. So why don't we go ahead and put that nicely into a statement. We will say that a function g, and I'm going to be using g here because this is what I see on the graph, but it could be f, it could be h, and these are just variables. And instead of a, I am going to be using c. So we are going to begin by saying that a function g has a jump discontinuity at, in this case, at x equals c if the following is true. Number one, the one-sided the one-sided limits exist. But number two, they are unequal. In other words, what this is saying is that the limit as x approaches c from the left of g of x exists, and the limit as x approaches c from the right also exists, but they happen to be different. So in a case like this, then we claim that the function g will have a jump discontinuity at x equals c. The last type of discontinuity, as I said before, is an infinite discontinuity. So right here. For a function to have an infinite discontinuity at a value of x, that means that as x approaches a from the left or from the right, we have some sort of infinite behavior. Maybe both one-sided limits approach positive or negative infinity. Or maybe just the left-handed limit approaches positive or negative infinity. The point is that around A, there is infinity involved. Look at the first case right here. Here A is 2. So when x approaches 2 from the left and from the right, the y values are going off towards positive infinity. Immediately, we have an infinite discontinuity at 2. In fact, we should already recognize this as a vertical asymptote at x equals 2. Then when we look at b right here, we again have some sort of infinity going on. The left-handed limit doesn't exist because the function goes towards negative infinity. That alone declares an infinite discontinuity at 2. But we have more discontinuity, more bad news. Also, the right-hand limit at 2 doesn't exist because the graph goes off to positive infinity. So indeed, the line x equals 2 becomes a vertical asymptote. So then that means that we have another case of infinite discontinuity at 2. Notice how now a vertical asymptote is a type of discontinuity. A vertical asymptote represents an infinite discontinuity. How nice. And look at this bizarre case right here. The graph is beautifully continuous on the left of 2. It is even left continuous over here. But then what happens on the right? On the right, the right-hand limit doesn't exist because the y values go off to positive infinity. Well, even though we didn't have an infinite behavior on the left of 2, just because we had it on the right, that means that we have an infinite discontinuity. So the line x equals 2, honestly, is a vertical asymptote. So now, writing the formal statement, the formal definition of an infinite discontinuity, we will say that a function f has an infinite discontinuity at x equals a if and only if one or both of the one-sided limits is equal to plus or minus infinity. So, for example, if you were to find that the limit as x approaches a from the left of f of x is equal to positive infinity or perhaps negative infinity, this is enough to say that the function has an infinite discontinuity at x equals a. And not only that, the line x equals a becomes a vertical asymptote. Let's look at example 1. It is asking us to discuss the continuity of the following piecewise function. I'm hoping that by now you know what a piecewise function is. I remember doing this with my with some of my students in pre-calculus 11. So practically what is happening is that for different parts of the domain, we are utilizing different functions. So when x is less than 1, we're going to be sketching the line y equals x. When x is between 1 and 3, including 1 and 3, the graph is going to be the constant function 3. And when x is greater than 3, we go back to the linear function x. Try to pause the video and see if you can sketch the graph before I show you how it looks like. So here you can nicely see the sketch of our graph, of our piecewise function. So you can see exactly that when x is less than 1, we are sketching the line y equals x. But because we are not including 1 for the line, we have an open circle. Then when x is between 1 and 3, including 1 and 3, we're sketching the horizontal line 3, the constant function. So right here you can see that. And then we stop that at 3. After 3, when x is bigger than 3, we go back to the line. And in fact, I should put an arrow below, an arrow above over here. So that's the graph of f of x. So this graph is dynamic. It has a lot going on. So we can really have nice discussions here. I'm going to focus on the transition points. I'm going to focus on the parts where I see closed dots and open circles. Because a line is continuous everywhere. So at these values of x, the function is continuous, a constant function is continuous, and the line again is continuous. So I just have to worry about the transition points right here. X equals 1, there's a lot going on there. X equals 3, there's also a lot going on there. So is the function continuous at 1? Is the function continuous at 3? What is happening there? Everywhere else, the function is continuous. So my only concern is what happens at 1 and what happens at 3. So let's go ahead and think about that. What happens at x equals 1? So in this case, I am hoping that you're noticing that at x equals 1, the function is not continuous. The function has a jump discontinuity. So we will say a jump discontinuity at x equals 1. How do we know that? Well, simply because the limit as x approaches 1 from the left of f of x is equal to 1. And if we look at the other limit, the limit as x approaches 1 from the right of f of x is equal to 3. But unfortunately, 1 is not equal to 3. So then that means that the limit as x approaches 1 from the left of f of x will not be equal to the limit as x approaches 1 from the right of f of x. So that is exactly the definition of a jump discontinuity. Now, something really nice to notice is that this function is right continuous at 1. It is not left continuous at 1 because the limit exists, but the function is undefined. No, I shouldn't say it's undefined, but at 1, the value of the function is not 1, it jumps all the way to 3. So it is not left continuous, but it is right continuous. So allow me to make a note of that. I'm going to say over here that f is right continuous at x equals 1. In other words, I know that the limit as x approaches 1 from the right of f of x is equal to f of 1. Okay, so that's pretty much clear. The limit and the value of the function at 1 from the right are equal to each other. All right, fantastic. Now let's go to x equals 3. what happens around x equals 3. So I noticed here that the limits, the left-hand limit and the right-hand limit are identical. And I also see that the function is beautifully defined at 3 and is on the graph. It's not somewhere above or below. So then that means that the function is completely continuous at 3. I have two-side continuity. So we will say that f is continuous at x equals 3. How do I know that? Because the double-sided limit as x approaches 3 of f of x exists, but on top of that, it is equal to f of 3. So that is exactly the definition of continuity. Let's look at example 2. What type of discontinuity is exhibited by the following function? I will try not to show a graph of the function because otherwise it becomes very straightforward. What I want is to help you reason through the graph just by using limits. I don't want to have the graph yet. I'm going to show you the graph a little bit later on, but later on. So let's start. Let's look at g of x. It has a numerator, which is a line, and a denominator, which is a line. Lines are beautiful. They have no holes, no jumps, nothing like that. The only thing here is that they are expressed as a fraction. I have a numerator and a denominator. So then if x is -2, the denominator is going to be 0. And we know that division by 0 is undefined in mathematics. So I already feel that when x is -2, I may have discontinuity. Any other value of x that is substituted into this expression will deliver a beautiful y value. The only x value that we potentially have a problem is with -2. So why don't we go ahead and analyze the function around -2 so that we can determine the type of discontinuity that we may have. So in doing that, let me begin by drawing the number line. I don't need the y-axis. So think of this as the x-axis. Here, let's say 0, 1, -2 right here. We are going to be focusing around -2. What happens on the left and what happens on the right of -2. All right. So let's start with the left-hand limit. The limit as x approaches -2 from the left of g of x. That means that this is the limit as x approaches -2 from the left of x minus 3 over x plus 2. So what is happening here is the following. As x approaches -2 from the left of -2, the numerator is going towards -5. So the numerator is going to go towards -5. That's not a problem. But the denominator is going towards 0. In other words, the denominator is getting very, very, very small. And because x is approaching -2 from the left, let's say something like -2.5 and so forth, when you plug in, for example, -2.5, -2.5 plus 2 is going to be negative. So I am going to have the effect of dividing a negative number, -5, over negative 0.00 something, so over something very small but negative. Let me just symbolically put a negative over here. And when I do that division process, -5 over something negative but very small, I am going to get something very, very large. And the two negatives are going to cancel each other out. So I am going to get positive infinity. So this limit end up going towards positive infinity as x approaches negative 2 from the left. So this is already enough for us to say we have an infinite discontinuity. Honestly, you don't have to continue with the right-hand limit, but I'm going to go ahead and do that just to get the full picture here. So now then, the limit as x approaches negative 2 from the right of g of x. So this is going to be equal to the limit as x approaches negative 2 from the right of the actual expression, x minus 3 over x plus 2. And when x is getting really close to negative 2 from the right, the numerator is still going towards negative 5. But the denominator is going to 0. But it is now going to 0 in a positive way. I'm going to put positive over here. And positive because since x is going towards negative 2 from the right, this x value will be a small negative value, so that when you add it with 2, the entire result will end up being positive, but a very small positive number. So negative 5 over something very small and positive will be negative infinity. So that's going to be over here, negative infinity. So I should expect that on the left of negative 2, the graph goes off to positive infinity. And on the right of negative 2, the graph goes down towards negative infinity. Anyhow, that means that G has an infinite discontinuity at x equals negative 2. And as I said before, I didn't have to analyze both limits. I only needed one. Just the first limit was enough to declare an infinite discontinuity, but I wanted to practice also a little bit more with you. So now let's look at the graph and see whether our conclusions are accurate. Look at that. So nice. So here we have, very nicely, let me point that out, the limit as x approaches negative 2 from the left. You can see it right here. And the limit as x approaches negative 2 from the right, you can see it right here. So you can see positive infinity on the left of negative 2, negative infinity on the right of negative 2.